Okay, homework 3 due on Friday. And I noticed there's already a couple of submissions on that assignment, so I took that as a good sign. And then our first exam will be on Monday. And I've told you all before what the parameters of the exam on Monday is going to be, and you've just had the second quiz, and so you kind of get a sense for what kind of problems you might see. So just to give you an idea, you had one problem for the quiz today. We'll probably have 3 problems of similar complexity. So just thinking about in the 50 minutes that we've got for the exam, I'm going to have a couple of concept questions, maybe 4 or 5 concept questions. They're brief. And then 3 problem-solving questions of about that complexity. So, we took 15 minutes for the quiz. Some people finished it in less than that. So if you make steady progress, then I don't think you'll feel too pressed for time in the exam. Today we're going to talk about sedimentation, and this topic is included in the exam, but you're not going to have homework problems that you submit before the exam. I've got an in-class exercise, so you're going to get some computational experience related to sedimentation. So sedimentation is fair game for the exam, but you just won't go through the homework cycle on it before the test. All right, so any announcement questions before we get into sedimentation? Okay, just to review where we're at, we've talked about some of the preliminary concepts of sizing, like how much water people demand. We've talked about issues related to the variability of water demand, coagulation, flocculation, softening, eye exchange, reverse osmosis. Now, these other steps aren't shown on this diagram because this is a diagram of surface water treatment, which is most common around here. And these other steps would be used either with groundwater sources in the case of softening. That's most common, that you'd need to soften groundwater. Or ion exchange is applied if you have some contamination or if you're doing an industrial wastewater treatment, or at individual homes at a point of entry or a point of use. But it's less common to have ion exchange for like an entire municipal water supply where it's surface water. And the same thing is true of reverse osmosis. Like, we don't have reverse osmosis shown in this process diagram because it's most likely going to be used in some place where they have a brackish groundwater, meaning a groundwater that has some salinity to it, or where they're desalinating ocean water to generate like the domestic water that's used. So places like Saudi Arabia, UAE, Dubai, they desalinate a large fraction of the water that they use, and so they're not going to have coagulation, flocculation at those spots. They're going to have a completely different water process. But this is just a kind of a schematic of what we would have in this area. And so what we're talking about today is the sedimentation step. And just to review this little conceptual animation, not sure why there's, that's intense. All right, so we have these large particles which have formed through the decreasing intensity of flocculation. Like, we have maybe multiple chambers where we're reducing the mixing energy, and the floc particles have grown larger, and then we just need some quiescent tank for them to settle to the bottom, where the keys are going to be that we have to manage the velocity coming out of the tank, because the velocity going out of the tank is too high, then it will suck the particles into the outlet. So we need to have some sort of a design that is a calm zone where these particles can settle downward, and then an effluent design that doesn't disturb that calm zone. Now, this is showing an important point, and that is those particles don't all have the same diameter. And we'll talk about the implications of that. Sometimes, just to simplify our calculations, we'll consider only a single particle diameter. But the reality is that there is a wide variation in not only particle diameter, but also particle shape. And that affects how quickly the particles can settle downward through the settling tank. So sedimentation can take between 2 hours to 8 hours, depending on the nature of your flocks. It happens in these the settlement basins, otherwise known as a clarifier, and we're removing the agglomerated flocks, which are mostly colloids that have been joined together as their repulsive charges were destabilized during coagulation. So some of the things that can help us achieve effective sedimentation is distributing the particles so that they're not all entering the tank at the same point. So somehow evenly distributing all of the particles and having a section in the tank where the water is moving very slowly and that there aren't velocity gradients that disturbs the downward movement of the flocks. Getting out of the tank without scour, and then some way, you can see here is a scraper at the bottom of the tank. It's almost like a squeegee. We need to have that moving at the bottom of the tank without disturbing the settlement that occurs above it. So as you might expect, this wiper at the bottom of the tank rotates pretty slowly, because if it's going around in circles really fast, then the particles wouldn't settle in the first place. Okay, so here's a cross-sectional view that shows a traditional circular horizontal flow clarifier. And in this horizontal flow clarifier, what happens is the water comes in at the center and it's distributed evenly, and so they may accomplish that through baffles or by having a lot of holes in a circular gate that surrounds the inlet pipe. The water is going out radially, and so it's going outwards towards the right and going towards this effluent weir, but it's also going outward to the left. It's coming towards us and also outward into the page. It's just if we look from above, the water is coming from the center and it's moving towards this outside edge in all directions. It's moving out. As the water is moving out, the particles that are suspended in the water are settling downward. So we've got both the movement of the water to the right and the movement of the particle downward. And so the net trajectory that's traced depends on the relative velocity of each of those vectors. How quickly is the water moving to the side? How quickly is the water moving downward? And so we go through a variety of calculations to determine the velocity of the particles that are settling. And then we also need to calculate the liquid velocity as it's going down. And what we assume is that if a particle reaches the bottom of the tank before it gets to the edge wall, then we assume it's removed. But if the water gets to the edge and it hasn't hit the bottom, just to be conservative, we assume that it gets sucked out through the effluent weir. The reality is probably somewhere in the middle. You know, there may be some particles that get to the edge of the tank and then slide along the side and get to the bottom. But it's only those particles that settle at the bottom of the tank that we assume is completely captured. The other type of settlement basin that we're able to load with higher liquid rates and therefore they use up less area in a treatment plant is an upflow clarifier. And in an upflow clarifier, instead of the liquid moving radially outward, the liquid is moving upward. And so in this example, the water, the bulk movement of the water was to the right, or I guess to the left, just always sideways to this effluent weir. Whereas here, in the upflow clarifier, the liquid's going up and the particles are going down. And so it's kind of like a terminal velocity problem where what you're hoping is that your liquid velocity upward is less than the particle settling velocity. And as long as that's the case, then the particles will settle downward into the sludge zone and you'll have effective removal of the particles. So upflow clarifiers we're able to load them more heavily because of that. I'll show you some general kind of rules of thumb and loading rates that clarify the difference between the two. There's a parameter that is a little bit counterintuitive, the overflow rate. And it has units of velocity. If you think about the units here, Q is cubic meters per second, and area is square meters. And so the overflow rate has units of velocity, so meters per second. But you have to be really careful in which area you use. It's the bottom area of the tank, which is counterintuitive because you might think if we're calculating a velocity, we'd need to know the cross-sectional velocity that the water is actually passing through. So you might be tempted to think that the area you should use is like this front face area. But that's not the case. It's actually just the bottom area of the settling tank that you use for calculating the overflow rate. And the overflow rate that you are aiming for kind of depends on the condition of the water before you treated it and what kind of flock size you're expecting to see. And the higher the loading rate, the larger you assume the flocks are, and the more easily they're removed. And so these lower loading rates, like if you had water that had high algae in it, algae particles are going to be very small in water, so they're more difficult to remove. The flocks are going to be smaller than if you had been treating water to remove turbidity. So the turbidity is those colloid particles which, when they combine together, are going to be pretty large flocks, and they can settle more easily, and so you can have a high loading rate. So if you think about what this loading rate is talking about, it's saying how many cubic meters per day you're putting into the tank relative to the bottom area of the tank that the settling occurs over. I think that this will probably make more sense as we work through an in-class exercise today and next time that I prepared, but you can see that an upflow tank typically gets away with a higher loading rate than does a rectangular horizontal flow clarifier. So in the horizontal flow clarifier, this is just another diagram that's showing the different parts of it, where the water comes into the tank with a pipe, and we need to protect this settling zone. We can't have a lot of turbulence and like countercurrent flow in this settling zone. It should be laminar conditions, ideally, inside of the settling zone so that the particles can settle downward without being disturbed. And so part of the way that we can help induce the settling zone is to have a baffle just in front of the inlet pipe so that the water that comes in isn't like a jet that is then causing a bunch of swirling and mixing inside the clarifier. Instead, this baffle, the water runs into the baffle and then is distributed downward. And then further, we have a perforated baffle on the other side of it so that the water is once again kind of just smoothed and distributed so that you're kind of spreading it out vertically through the entirety of the tank. You can see the sludge zone, which is where you've got a wiper that's kind of pushing the sludge into some sort of a trough or a hopper, and then an effluent weir that has hopefully slow velocities. Typically the inlet zone is about 1.5 meters before the settling zone takes into effect, and how big the settling zone needs to be depends on what kinds of particles you expect to be forming with your range of water characteristics and the coagulants and flocculation that you're going to be doing before this. The sludge volume, the volume of the sludge zone, it's usually about in the first 1/5 of the clarifier that the most of the volume settles. But there are going to be really small particles that take the entirety of the clarifier to settle. Even if they don't contribute much to the mass, they would have a pretty disproportionately high effect on the turbidity if they were allowed to escape. And so it's really important to differentiate between the mass of the solids that are removed and the number of particles that are removed. Because at the beginning of a clarifier, what's going to settle out at the beginning is the really heavy particles that were large and dense. Those will settle down through the water easily, but there's going to be a lot more of the small particles that don't have a lot of mass because they're small in diameter, and so the removal efficiency depends on overflow rate. So let's talk about the settling velocity and some of the factors that determine that. It depends on the density of the particle, it depends on the fluid characteristics, and it depends on the diameter of the particle. And so those are the main factors that determine how quickly something settles downward. You can see that this is just showing typical settling velocities in meters per second. And so a diameter, 1 millimeter diameter grain of sand would settle down at, what's that, 0.2 meters per second? So 0.2 meters per second, that's pretty fast. But as the particles get increasingly small, the settling velocity gets much, much smaller. So to be completely removed from the tank, we already said this assumption that it has to reach the bottom of the tank before it gets to the side edge. That if it gets to the edge and is above the bottom of the tank, then to be conservative, we have to assume that that particle escapes. So if a particle has a certain settling velocity and a tank has a certain overflow rate, so remember, overflow rate is the liquid loading rate Q divided by the bottom surface area of the tank. So if you have a certain overflow rate and a certain settling velocity, then you can calculate the percentage of particles that are going to be removed according to this formula. And so what that means is that if you want to have 100% settling, then you should ensure that the liquid loading rate, let's see, what would give us 100% settling, is a settling velocity that's equal to the loading rate. But not all particles have the same settling velocity, and that is because they have different diameters. You're going to have out of the flocculator some particles with a small diameter, some particles with a large diameter, and so they'll all have correspondingly different settling velocities. And there's different types of settling. On Friday, I'm going to talk to you about type 2 and type 3 settling. But the simplest of the different settling types is when a particle is settling downward and it doesn't encounter any interaction with other particles. It's not bumping into other particles along the way. It's just settling in isolation. So terminal velocity is how we calculate the settling there. It's just a certain particle that's in equilibrium with the gravitational forces, the buoyant forces, and the drag forces. So this diagram is showing each of those. And it reaches this terminal velocity instantaneously, really. As soon as the particle enters the tank, it'll start settling downward and really quickly come into an equilibrium where it's settling downward, but it's not constantly getting faster and faster. It reaches that terminal velocity where the drag forces are equaling the difference between the buoyant and the gravitational forces. So the settling velocity depends on the drag coefficient of the particle. That's C sub d, the drag coefficient of the particle. G is gravity. We've got the density of both the solid particle and the density of the liquid in this formula, and then the diameter of the particle. If we assume that the particles are spherical, and if we assume that it reaches the terminal velocity really quickly, then we can simplify this settling velocity equation by applying Stokes' law. And so this is Stokes' law, which says that the settling velocity depends on the gravitational constant, the difference in the density between the solid particles and the liquid, the diameter. Now this is assuming it's a sphere. And that's an okay assumption in a flocculation basin. Some of the particles won't be spherical, and those particles will settle at a different velocity than is predicted. And so this model isn't perfect in predicting what's going to happen inside of the settling basin, but it does a fair job, and its simplicity is hard to argue with. And you'll notice that the viscosity also is one of the terms here. So the viscosity of the fluid varies as a function of temperature, and that'll usually be given to you in a problem statement, like which viscosity you should use. Okay, so we don't have time to start on this one today, but I am going to get it into your hands. Well, I don't know. Should I hold on to it till Wednesday so you don't lose it? Friday. Today's Wednesday, right? Yes. Okay, I'll hold on to this one. This is what we'll start with on Friday, is this settling example, but it is in the notes, which are posted on Blackboard. If you simply can't wait, you go ahead and get started on that example. We'll work on it Friday. And look for that email that I'm going to send you related to the volunteering opportunity this Saturday morning. All right.